I'm sure that we've all enjoyed blowing bubbles, probably when we were a little younger. It's one of the sort of experiments where you get a perfect result every time, namely a spherical shell of liquid with air inside and air outside. And young people have been blowing bubbles for a long time. I'm sure everybody here blew bubbles, and your parents blew bubbles, and their parents, going back almost to the beginning of time. And in a few years' time, or maybe already, your children will blow bubbles, and in turn their children will blow bubbles until the world comes to an end. There's something sort of magical about bubbles. Everybody from the sort of humblest member of Canterbury Society to directors of electronics, the Queen, Prince Charles, etc. They've all blown bubbles in their time. You don't have to be British to blow bubbles. They blow bubbles in the United States, Africa, China, even Australia. But of course the bubbles there are upside down. But bubbles sort of penetrate the whole of science, you know. In our food and drink, there are bubbles and films, etc. Those of you with boats will understand cavitation, where bubbles are produced by the propeller that drives your boat. This causes lots of trouble and reduces the sort of driving force, and causes sort of the propellers to wear out, etc. And so a lot of research is going into this. But it can be good in the sense that maybe some of you here have had kidney stones. If you go to the hospital, one way of dealing with these is to use ultrasonics in order to produce sort of cavitation, that's namely lots of bubbles around your kidney stone, which will break it up and make it eventually disappear. But if you look, you know, at the sort of microscopic world of bubbles, or in the early days of fission, the liquid drop model was introduced to explain fission, where a nucleus breaks up into two smaller nuclei. And it was thought that it behaves in the same way as a drop. If you excite a drop and cause it to go into vibration, it will break up into two drops. And the physicists here will have heard of bubble chambers, and the electronics people will have heard of bubble memories, etc. It sort of percolates the whole of science. The clouds, of course, are made up of droplets, and I'm told by astronomers that the distribution of galaxies in the universe resembles very much a sort of foam, a foam produced by basically lots of bubbles. So, I mean, all scientists have been interested at one time or another in bubbles. The chemists, of course, have been interested in sort of chemical properties. If you go to any supermarket, they make lots of money by selling you bubbles in the form of washing up liquids and detergents. So there's a big chemical industry that has grown up around the bubble, basically. The physicists are interested in sort of physical properties of bubbles and molecular forces that causes sort of stable bubbles. And our colleagues in mathematics are interested in bubbles because they produce analog solutions to very difficult mathematical problems. So they can see what solution they should obtain analytically, but there are lots of problems where remain still unsolved. And biologists, of course, are interested in bubbles because the sort of lipid membranes that form the surfaces of our cells and the plant cells have a molecular structure very similar to bubbles, and so a lot more research has gone into bubbles as well as these so-called lipid membranes. And our colleagues in the arts, who live somewhere over there, they're also interested in bubbles. If you go to any respectable art gallery, if it is indeed respectable, it will have at least one painting depicting a soap bubble. And perhaps the most famous painting is the one by Sir John Millais that was used to advertise Pears soap over 100 years ago, of a young boy blowing bubbles. And in those days it was done with a sort of clay pipe and a bowl of soap solution. But there are many other paintings. They're largely unknown, because they weren't used to advertise anything. So I'm going to start off by drawing your attention to one or two of these paintings. If we can turn the lights out. Right. If you look very carefully in the first slide here, the one thing that you will notice about it, if you look very carefully, is that there are no bubbles. This I usually use as my sort of commercial when I go to schools to give a talk. But the next slide contains the famous painting by Sir John Millais of the young boy blowing bubbles here with a clay pipe and a bowl of soap solution. The bubbles haven't changed very much in the intervening years. This painting in fact became an embarrassment to him, because when he grew up he became an admiral in the Navy, and when I think it was George V came to visit him, he had to explain away this painting. Anyway, this painting, everybody I think has seen this painting many, many times. It's been used by cartoonists to draw attention to the antics of politicians and all kinds of other people. And the next slide comes from the Times newspaper and contains a cartoon of somebody who you may remember from long ago. Right? Right, but as I said, there are many other paintings of bubbles, and if we go back a few years, here's one by the painter Manet on exactly the same theme of a young boy blowing bubbles. Going back further, this is by Chardin on exactly the same sort of theme. Most of these paintings were painted during and after the Industrial Revolution, when soap was produced on a large scale. Everybody could afford to buy soap and everybody could afford to blow bubbles. The next slide is from about the time of the Industrial Revolution, some fairly wealthy children blowing bubbles. If you try and look for paintings from an earlier period, they're much rarer, because soap was produced on a small scale and was relatively expensive. But if you go round the galleries, you will from time to time encounter a respectable gallery that has one of these paintings. And the next one comes from the Italian school, is perhaps 100 years older than this one. Right? And if you look carefully, you can see the bubbles. Right? And now we're back to somewhere where you will remember Canterbury Westgate Towers, and now we'll turn the lights on and we'll get down to the sort of serious subject of the science of soap films and soap bubbles. And in order to draw attention to some of the properties, I produced some sort of bubble solution here. Basically, it's just a bin with cold water, and then I've added about a third a container of some washing up liquid. This was produced by somebody you may know, Mr. Purcell, but any other one is okay, you know. And then you just pour it in here, and then with a scientific instrument that I brought all the way from home, not knowing whether here in electronics or in the university they have one of these, so I always bring my instrument along to stir up the solution, right? Okay, and with this solution, and one can produce some large films and bubbles. For instance, if I dip this circular ring into the bubble solution, you probably guess that what I get is a sort of disc of soap film. So you won't be surprised if I get a sort of disc of soap film. But these large soap films have a sort of magical property that small soap films don't possess. And this magical property will hopefully appear within the next 60 minutes or so. The thing about these large soap films is that they are much more flexible than the smaller soap films. So if I vibrate it like this, it's vibrating in its sort of fundamental mode, like a sort of violin string, but with a very large amplitude. And I don't think anybody will have any difficulty in seeing this vibration, right? In the case of a drum skin, it behaves in exactly the same way, but the amplitude of vibration is so exceedingly small that you can't actually see it vibrating. However, the drum skin, when you vibrate it, it sends a sound wave to your ear, and your ear communicates with your brain, and you hear a sort of low note. But with the soap film, which is vibrating at about 1 vibration a second, 1 hertz, this sends a sound wave to your ear, but at this frequency your ear doesn't communicate with your brain, and so you can't hear it vibrating. But the nice thing is you can, there's no difficulty in seeing it vibrating. Right? This is the sort of fundamental mode, but then if you vibrate it at higher frequencies, you can get more complicated modes, or sort of 2 jellies going up and down in antiphase. Right? If those who've studied violin strings will know you get in a violin string you get a sort of 1-dimensional version of this. And if you vibrate it at higher frequencies, which is difficult to do by hand, you need some vibrator, you can get more oscillations. Well, to illustrate the more general case, I brought along this wave machine here, and Nikos is going to help me demonstrate this. Right, you just sort of stand there, hold that. Right, you come a bit nearer. Stop. Okay. Raise it up a bit. Okay. I'm going to pull on this end, you pull on that end, right? If I cause a disturbance to happen at this end, it will travel down the wave machine, and when it gets to Nikos, it will decide it can't go any further, and it will turn round and come back again. Right? And if we produce 2 of these, they will interact with each other. Right? But if we continue to vibrate them, we can set up a sort of standing wave pattern. You can see there are certain regions where the sticks are vibrating with quite a large amplitude, interlaced by regions where the sticks are hardly moving at all. And we had this is what happened with the soap film, with the 2 sort of jellies going up and down in antiphase. If we increase the frequency of vibration, then we'll get more of these regions. Okay. Alternatively, if we reduce the frequency, we'll get fewer of these regions. Okay, can we put this flat on the ground, do you think, so I can wrap it up? Okay. Okay, I think it will come. Okay. Oh, thanks very much indeed. Thanks very much. Okay, well, this is very interesting, but I don't want to concentrate on this. I want to draw your attention to some other properties of soap films. And one of the interesting properties of soap films is that, in fact, the energy of a soap film is proportional to its area. And any system, when it comes to rest, always takes up the configuration with the minimum possible energy. And since the energy of a soap film is proportional to its area, the soap film will always take up a surface with the minimum area. Now, in the case of a ring, this is fairly obvious that when it comes to rest, it doesn't sort of vibrate like this. Well, that wouldn't be rest, would it? Or it doesn't have any exotic shape. It takes up the shape of the disc. But this is a very general property of the soap film, and it doesn't matter what the shape of the boundary is, it will always find the surface with the minimum area, which is also the minimum energy. So if we introduce, say, a piece of thread going from here to here and break the soap film on this side of the thread, there'll be no soap film on this side, but there will be one on the other side, and it will want to take up the smallest area, and it will do this in fact by pulling the thread into the form of an arc of a circle. So if I break this, or it all broke, if I do it at the beginning it should last. I break the soap film here, again. Well, right, there's no soap film here, and the thread has been pulled into the form of an arc of a circle in order to minimise the area of the soap film and of course maximise the area of the hole. Right, so this is another example of the fact that the soap film likes to take up the minimum area. If we extend that to a closed loop of thread, I've got a closed loop of thread here, right? If I produce my disc of soap film, break the soap film inside the loop, there'll be no soap film inside the loop, there'll be one surrounding it. We want to take up the minimum area, and it will do that by pulling the thread into the form of a perfect circle with no soap film inside. Right, so we start off by producing the disc here and break the soap film inside the thread, then try and release the thread without breaking the rest, without breaking the rest of the soap film. Right, and you can see this thread has been pulled into the form of a circle in order to minimise the area of the soap film and at the same time maximise the area of the hole. Right? So these are a few simple demonstrations that the soap film likes to take up the minimum area surface. If you extend this to the case of the surface connecting two rings, you might think the minimum surface would be a cylindrical surface, but it was found a few years ago by Mr. Euler that this was not the case. The soap film that forms the minimum area surface is a catenoid, which has a sort of neck in the middle, and the soap film will automatically take up this shape in order to minimise its area. When they're very close together it may look cylindrical, but as I bring them further apart you can see a neck forms in the middle, and there's a critical separation at which it will break up into two discs. Right? And for further separation the minimum surface is two discs. This is a problem that undergraduates used to solve when I was an undergraduate, but now probably it's postdoctoral work. Anyway, so you can see just by dipping frameworks into soap solution you can produce these sort of minimum surfaces that are of great interest, particularly to mathematicians. Now let's extend this to more complicated problems. Here is a more complicated frame. This is a tetrahedron, has 4 faces and 4 corners and 6 edges, right? If we dip it into the soap solution, we'll get a soap film with the minimum area connecting the 6 edges of the tetrahedron. And at the first guess, you would think that it's going to fill the 4 faces of the tetrahedron. Well, if that is the minimum surface, then that's what we'll get. But if there's a surface with a smaller area than that connected to the 6 edges of the tetrahedron, then the soap film will automatically find it for us. So all we need to do is to dip it into the soap solution to discover the minimum surface. Right, and we see that it produces this interesting surface that goes inside. There's a single point inside at which lines of soap film from each vertex of the tetrahedron meet. There are 4 of these lines meeting at a point there at a very precise angle, and each line, if you look very carefully, each line is formed by the intersection of 3 surfaces. There's a model here. This aluminium tube represents the line of soap film, and these cardboard pieces represent the surfaces, and you always get, for minimum surfaces, 3 surface soap films meeting along a line, never 4 or 5, because that gives rise to a larger area. And they always meet at a fixed angle of 120 degrees. These angles are all 120 degrees. In the case of the tetrahedron, all these lines are straight lines, but we'll see more generally that they can be curved. And as a consequence of this, you always get 4 lines meeting at a point, and they also meet at a fixed angle. The angle between any two lines is 109.47 degrees. This is well known to chemists. It's the tetrahedral bonding angle associated with the molecules in the form of tetrahedra, in which you have atoms at the corners of a tetrahedron and one at the center, right? And the angles that the atoms make is this tetrahedral bonding angle of 109.47 degrees. So this is the minimum area contained by the 6 edges of the tetrahedron. If you break one of these surfaces, then now there's no connection to the bottom edge, and we end up with the minimum surface contained by the remaining 5 edges. And you can see here we've got a curved line of soap film with 3 surfaces meeting at every point along that line. If you go one stage further and break the connection to the top edge, you get the minimum surface contained only by 4 edges, the 4 edges that I'm not holding, and we have a sort of saddle surface here, right? Okay. Well, in order to throw some light onto this problem, we are going to turn the lights out, right? Okay. Now I can project this soap film onto the screen here using sort of shadow projection. You can perhaps see it's much bigger now. You can see the point at the center and the lines very clearly here. Right. Okay, let's put the lights up again. Okay, well, these demonstrations have been carried out with all kinds of frameworks. In the case of the cube, which has 12 edges and 8 corners or vertices and 6 faces, you might think that the minimum surface would be a series of surfaces all meeting at a point at the center, as in the tetrahedron. But if that was the case, you would have you wouldn't have 4 lines of soap film meeting at a point. And one of the conditions for minimum surfaces is you've got to have 4 lines meeting at a point. So how do you form the minimum surface with 4 lines, only 4 lines meeting at a point? Right? Well, the way to find out is to just dip it into the soap solution and bring it out, right? And we end up with this minimum surface here with a sort of square in the center. Here the square is parallel to the horizontal faces of the cube. But if I perturb it, it's now parallel to a vertical set of faces, or this vertical set of faces, right? And you can see at the corners of that square, you've got 4 lines meeting at 109.47 degrees, etc. Right. Now, let's examine the square in a bit more detail by turning out the lights. Oh. Right, if we look at that square, the sides there are slightly curved. That's because the angles here have to be 109.47 degrees and not 90 degrees. Right? Right. This is not a proper square because the sides are slightly curved, so these angles are 109.47 degrees. Okay, let's put the lights up again. So we saw in the case of this the cube, the surface is sort of threefold degenerate, with the square being parallel to any of the 3 different orientations of the faces. When you come on, well, let's perhaps do this one next. This is a triangular prism with a triangle at the top, triangle at the bottom, connected by vertical edges. Not obvious what the minimum surface is here, so we'll dip it in. and we get this minimum surface with a line through the centre there, and at the bottom of that line we've got 4 lines meeting at a point at the angles of 109.47 degrees, and at the top as well, etc. And from each vertical edge there's a vertical soap film going in to the centre, and there are 3 of these meeting along the line at the centre. When you come on to more complicated frameworks like this one here, the octahedron, which also has 12 faces and 6 edges, it's possible to have more than one minimum surface. You remember, a minimum is like being at the bottom of a valley, and these complicated functions, as you distort the surfaces, you can have several valleys, and each surface that you get, each equilibrium surface, is associated with being at the bottom of a valley. And so there can be several minima. The one with the greatest symmetry looks very much like a star. There's a single point at the centre, and emanating from the centre are 6 kites of soap film. Right, here it is. Right, you can see at the centre there are 4 lines meeting at 109.47 degrees, and then there's a kite here, kite up here, and 4 round the middle there. Right. Okay, perhaps if we look at that in projection, turn the lights out. Oh. Right, I've got a little few bubbles there, but you can see at the centre here there's a single point. You can see the kite here, kite up here, 4 around the centre. See if I can do that again. Quite a complicated surface. Okay, if we turn the lights on, as I said, there are several minimum surfaces associated with the octahedron. If we turn the lights off, we've got a surface with a square in the middle here. If we turn the lights off, right, you can see a square here, caught a little bubble there. A square with angles of 109.47 degrees. Ooh. Okay, here's another surface with a 5-sided figure in the middle here. Non-regular pentagon. Okay, so if you put the lights on, if you're interested in the smallest surface, then you have to determine somehow the area of all these surfaces, equilibrium surfaces, and pick out the one with the smallest area. Okay, well, these results about 3 surfaces meeting along a line 120 degrees and 4 lines meeting at a point at 109.47 degrees also apply in the case of bubbles trapped inside frameworks. So we can produce a bubble inside the tetrahedral framework by first forming the minimum surface, then dipping it in again partially, and we'll trap some air in the form of a bubble. Right, here's the minimum surface that we had before. So trap some air under there, and we'll produce a bubble that will take up the sort of symmetry of the tetrahedron. Right, it's sort of trapped by all these surfaces pulling it towards the edges. And at the corners of the bubble you've got 4 lines meeting at 109.47 0.47 degrees, and the edges of the bubble curved lines formed by three surfaces meeting at 120 degrees. And it's being constrained by films pulling it towards the edges. If we try and break these constraints, then eventually we'll be able to free the bubble from the framework. And when it's free, of course, it becomes spherical, right? Okay, here I've got a straw from one of Mr. MacDonald's shops. Right? If it's wet, we can poke it through the bubble and the bubble won't burst. If it's dry, the bubble will burst. Right? Now if I suck on this, right, I can suck the air out of the bubble. And if I blow, I can blow a bubble, right? Another way of highlighting these bubbles was introduced into this country a few centuries ago from the New World and has proved exceedingly popular, and consequently it's heavily taxed. But anyway, for scientific reasons we can demonstrate some of its properties. We can blow some smoke into the bubble, right, and this will help to sort of highlight the bubble. I don't want the electronics laboratory burned down yet. Okay, so you have to have a wet straw. Right, you can see the smoke is trapped inside the bubble, can't escape from the bubble. If you want to see what wonderful things this can do to your lungs, we'll turn out the lights, right? You can see it's all trapped inside there. Right, put the lights up again. Right. And we can do the same sort of thing with the cube. If we trap a bubble inside the cube, we'll get a sort of cubic bubble. Right? Okay, if we turn the lights out a second. We'll put the lights up again. Right. Bubbles quite like carpets actually. It's bouncing around on the carpet for a little while. With the triangular prism, prism we'll get a sort of triangular prism bubble. Okay. Okay. Right. And with the octahedron, an octahedral bubble. But one of the nicest bubbles that one can produce is the one associated with this framework here, which is a regular dodecahedron, has 12 faces. Each face is a regular pentagon, and the angles here are 108 degrees. Well, 108 degrees isn't very different from 109.47 degrees. And if we produce a bubble inside, it looks like a copy of the dodecahedron, but in fact the edges are not perfectly straight. They're slightly curved, like in the square inside the cube, in order to produce the angles of 109.47 degrees. But it looks like a sort of gemstone trapped inside the dodecahedron. If we turn the lights out, we can see it in projection there. Okay, put it up, the lights up again. Oh, let's perhaps do this once more. Okay, let's look at it without the smoke. Turn the lights out now. Okay, let's put the lights up again. Okay, so you can see you can solve these quite difficult mathematical problems by using this sort of analog solution, by dipping frameworks into soap solution. Okay, on these occasions I'm often asked, you know, what is the biggest bubble you can produce? Well, if you're going to produce a big bubble, you can't produce it by blowing, because we'd all have to blow for a week to produce a big bubble. So you have to think of a sort of new technology for producing big bubbles. So I brought something along here to produce big bubbles, right? And the nice thing, you have to have a big lecture theatre to produce big bubbles. I've got this device here dipping into some concentrated soap solution with some glycerin in it, right? If I bring it out, let it drain away a bit. Right, if I open it up, you can probably see a large film there, right? If I wave it around, let's do that once more. Open it up, then sort of wave it around and close it up again. Ooh. Okay. Yeah. Ooh. Okay, I've also got this other device over here. This is a sort of circular trough, and I've got a sort of ring dipping inside it, inside this circular trough, which contains some of this concentrated soap solution with some glycerin in it. And then when I bring it out, if the gods are with me, I'll get a sort of cylindrical film or bubble. Okay. So I'm going to ask Hannah if she'll come up. Will you come up? And we'll surround you with a soap film. Okay. Okay, what you have to do is stand in the middle, right? Face, yes, with your hands by your sides, right? And I'll just bring this up, and you won't feel anything, hopefully. Okay, thanks very much indeed. Right. Okay, very good. Okay. Okay, well, I want to now remind you of some mathematics, etc., that you probably learnt about in primary school. Right, this is the result about the shortest path connecting 2 points or 2 places. We all know that the shortest path is the straight line path, and any wiggly path connecting them has a greater length than the straight line. And we use this sort of every day in going from, I don't know, from our home to university or to school, etc., etc. But the people who build roads have forgotten about this. But we try and keep more or less to the straight line path, right? Now, if we try and generalize this and ask what is the shortest pathway or roadway connecting a number of places or a number of towns, it's not immediately obvious. We know what the answer is for 2 towns, it's the straight line. But what is it if we have 3 towns or 4 towns, etc.? And it's quite important because in building roads, etc., you can sort of minimize the cost by building the roads along the shortest possible path or connecting these towns so that it's possible to drive from any town to any other town. Well, let's focus on a particular case, what appears to be a relatively simple case of, say, 4 towns arranged at the corners of a square. It's not obvious what the minimum path or minimum roadway connecting these towns is, so that we can drive from any town to any other town. So let's explore a few possibilities. What happens if we join all these towns up by straight lines, right? Assuming that the square has unit side, right? It's not too difficult to work out the overall length of road required is 6.83 units. But hopefully we can find a roadway which is much shorter than this, and if we can, then that's going to cut costs, because the cost of building a road is proportional to its length. Perhaps a sort of circular roadway would have a shorter length than 6.83, right? And indeed it does. It has a length of 4.4, right? And it's still possible to drive from any town to any other town. Now, if we use the one result that we learned about in the cradle, the shortest path connecting 2 towns is a straight line, and replace this longer curved road by a straight line road. If we do that between neighbouring towns, of course, we're going to end up with 4 sides of a square with an overall length of just 4 units. Can we do any better than this? Well, little thought will tell you that we don't in fact need all these roads. We could eliminate one of these roads and it would still be possible to drive from any town to any other town, and the overall length would now be 3. Of course, it's a bit inconvenient if you want to go from B to C. You have to go all the way around, but the people who build roads, the chap in the cartoon there, for example, he's mainly interested in cutting costs, and so he would go for this roadway rather than the 4 sides of a square. Can we do any better than this? Or perhaps on the grounds of symmetry of the square, you might think that the crossroad system would have a shorter length. And so if we build a roadway in the form of a crossroads like this, we end up with a length of just 2.83 units. Well, Well, now we would like to know or be able to prove that this is either the minimum roadway connecting these towns, or to prove that it's not the minimum and try and find out what is the minimum. Well, this is where soap films can help us. You remember, soap films have the property, they always take up the minimum area. And so if we can convert that property into a minimum path property, then we could possibly solve this problem. Well, it's not immediately obvious how to convert a minimum area problem into a minimum path problem. So let's go back to the one result that we know and love, the one about the shortest path connecting two towns, and see if we can solve that using soap films. Well, the way to solve that, in fact, is to construct two parallel plates like this, connected by two pins perpendicular to the plates. Then if we dip this system into some soap solution, then we'll get a soap film inside that's bounded above by one plate and below by the other plate, and by symmetry it will be perpendicular to the plates, beginning on one pin and ending on the other pin. And so the actual shape of the tape of the soap film will be the same as this piece of tape, constant width equal to the distance between the plates, beginning on one pin and ending on the other pin. And when it comes to rest, it will take up minimum area, which in this case, because the width is fixed, the minimum area is the same as minimum length, so we should end up with the minimum length, the straight line path. Well, let's see if we do. I'll dip it into some soap solution here, right? And let it drain a little, and then put it on the overhead projector, and you can see it quickly takes up the straight line path. And if we perturb it, it always comes back to the straight line path. So I think you can see how we're going to solve the four-town problem. We're going to construct two parallel plates, but this time with four pins arranged at the corners of a square, right? And the same argument will tell us that we'll get a tape formed inside, and when it comes to rest, it will come to rest with the minimum area, which is also the minimum path. So all we need to do is to dip it into the soap solution and wait for the soap film to come to rest, and when it does, we'll end up with the minimum path connecting the four towns, right? And you can see that when it comes to rest, we end up with this configuration here with two three-way intersections. And if you look very carefully, all these angles look the same. That's because they are the same. They're all 120 degrees, the angles at which soap films meet. And if we work out the length of this, it turns out to be less than 2.83 of the crossroads. It turns out to be 2.73. Right? There are, in fact, two solutions to this problem. This is solution number one. Solution number two is this one, right? Which is exactly the same, except that it's turned through 90 degrees, right? If we wanted to find the minimum roadway connecting only three towns, we wouldn't want a connection to the fourth. And when it comes to rest, we'll end up again with three roads meeting at a point, and all the angles here being 120 degrees. Right? If we go one stage further and break this, we're back to the two-town problem. So in this way, you can get analog solutions to some of these sort of complicated roadway problems. In the case of 5 towns, right, in the form of a regular pentagon, all we need to do is to dip it into the soap solution. Let it come to rest. And we end up with three-way intersections here, all the angles being 120 degrees. And if we break some of these connections, we'll end up with the minimum roadway connecting these four, again with three-way intersections. And in the more complicated problems, like which are analogous to the octahedron problem, in the octahedron problem there were several minimum surfaces. In the hexagon problem here, there are several different roadways, and if you want to find the roadway with the smallest length, you have to work out the length of each minimum and pick out the one with the smallest. So let's dip it in one particular way and get one of these minima. Let it drain a little. Right. Here is one of the minima, again with intersections with all the angles being 120. And you can recognize this again by its symmetry. You need to rotate this through 180 degrees, so this hole goes into this hole to get the same configuration, right? That's one of the minima. It has twofold symmetry about a central axis here. Now if I dipped it in some other way and brought it out, I might get another minimum. Alternatively, I can get it to jump from being in one minimum to being in some other minimum by perturbing it, blowing on it. Right? And we can recognize that we've got a different minimum now because of the symmetry. This has a threefold symmetry about this axis here. You've got three sort of holes here. You only need to rotate it through 120 degrees. Right? And knowing the angles are all 120, it isn't too difficult to calculate the length of this. And finally, there's one rather trivial minimum, namely this one, right, which goes round 5 of the sides. Right? So I'll leave it as an exercise for you to calculate the length of each of these and pick out the one with the smallest length. Right? So you can solve these problems in this analog fashion very nicely. And here, if we bring it down to earth, so to speak, I've got on these plates a map with some towns: London, Bristol, Manchester, and a few foreign buzz up there. Right, so if you dip this into soap solution, there's only one minimum here. We'll end up, hopefully, with a number of three-way intersections. Right. We've got one just below Birmingham and one just to the east of Glasgow there. Right? I mean, this is a first guide to building roadways. I mean, there are some people who don't like roads going through the house, etc., etc. So there are other constraints, but it's a first guide, right? And it's also applicable to pipelines and cables, etc., etc. Okay, so finally, I want to say a few words about the interesting colours that appear in soap films. Ooh. Well, don't know where I'm going to leave this there. If I produce a freshly formed soap film, you might think that it consists of two parallel faces, but a little thought will tell you that since it contains water and soap, which are sort of draining under gravity, it's slightly wedge-shaped. So if you shine light onto it, say red light, some of it goes inside and is reflected from the back face, and some of it is reflected from the front face. Here, oh, I've got some bit wet there. Right, but you probably remember light is a sort of wave form, so these are really waves, and on occasions, if the conditions are right, the waves will add up, and on other occasions they will cancel out. And in the next transparency, that's the next one, or this one, I've drawn them as waves, right? And the two emerging beams, depending on the thickness of the soap film, sometimes will add up and produce a very bright fringe, and sometimes will cancel out, and you'll just get a black nothing, right? Well, we're going to examine a draining soap film. Draining soap film starts off being having a relatively large wedge angle, but as it drains and the soap and water drain out of it, the angle of the wedge becomes smaller and it becomes thinner, etc. It may start off having a thickness about 10 times the wavelength of light and then thin down to about the wavelength of light, and if it doesn't burst it will end up being about 1/100th of the wavelength of light, and that means it will only contain 2 ions, soap ions, back to back, so it's exceedingly thin. You can't have anything really much thinner than that. And if you examine the fringe pattern, the interference pattern, as it drains, you find initially there are lots of fringes, bright, dark, interlacing fringes, and as it drains, these spread out, and eventually when it gets less than the wavelength of light, you get destructive interference, and the soap film goes black, and if you wait long enough and it doesn't burst, the whole soap film, using reflected light, looks black, meaning that none is reflected and it's all transmitted. Well, I've set up a little demonstration to illustrate this, in which I'm going to shine light from a slide projector onto a soap film and catch the light reflected from the front face and the back face and focus it onto a screen there, and we'll see the change as it drains. These fringes change, and eventually the soap film goes black. Okay. Well, I have the setup over here. This is the slide projector, right? I'm going to shine initially red light onto a soap film, which I'm going to produce in this circular orifice, and the light from this soap film here is going to be reflected and go through this lens onto that screen, right? I'm going to move this out of the way. No. And we're going to turn the lights out, right? And you have to look at the screen. You can see here a sort of black hole. That's where I'm going to produce the soap film. And because I've only got one lens here, the soap film that you'll see is going to be upside down. So the top of the soap film is going to be at the bottom of the screen. Right, you can see these horizontal fringes here that gradually spread out. It's draining upwards because everything's upside down. This is the top of the soap film. This is the bottom of the soap film. Initially we had lots of fringes, now it's drained. The top of the soap film is not now going black here, right? And that, if the soap film doesn't burst, that will spread all the way down the soap film, which is, oh, something's happened there, up the screen. Right, you can see a little black piece there of the soap. That's the top of the soap film. And if we wait a little, or it will grow, start to grow, and eventually if the soap film doesn't burst, the whole soap film will go black, right? Perhaps it's worth doing that again. Right, with a new soap film. Oh. Right, you can see lots of fringes to start with, and then as it drains, these spread out more and more, and there are fewer and fewer fringes in view, etc. We're also getting some convection effects. I mean, it's difficult to control things perfectly here because all the fan here is causing air currents. You can see the black film forming at the top of the soap film, which is the bottom of the screen. Right. Okay, well this is the story of shining red light onto the soap film. If you shine white light onto the soap film, white light contains all the colours of the spectrum, and we get a superposition of all the fringe systems from all the different colours that make up white light. But the story about the black film forming at the top of the soap film, the bottom of the screen, still holds. So what I'll do, I'll break this soap film and then shine white light onto the soap film, and we'll get a superposition of all these colours. Right? See, this is the top of the soap film again, and you can see as it drains, they spread out, etc. And eventually we'll get some, well, these are some convection effects there, but eventually we'll get some black film forming at the bottom of the screen, which is the top of the soap film. Okay, well, I don't know how long we're going to have to wait for this, but this soap film is in fact mounted on a motor. And when I switch on the motor, the soap film will rotate, and instead of draining vertically under gravity, it will drain radially, and that means instead of getting horizontal fringes, we're starting to get some black film there, instead of getting some horizontal fringes, we'll get some circular fringes which will change colour as the thickness of the soap film changes. So I'll break this and produce a freshly formed soap film, right, and then I'll switch on the motor, and you should start to see circular fringes here, right. They change colour as the thickness of the soap film changes. The thinnest part of the soap film is in the centre there. I don't know if we're going to get any black film forming there. If we were to stop this, it will want to go back to producing horizontal fringes, right? It's trying to produce horizontal fringes that we had before, right? Perhaps worth doing that once more. The colour's changing as the thickness changes, and as it drains radially. If I switch it off there, right, you get all these nice colours coming back again. Okay, let's put the lights on, shall we? Okay, so I hope I've been able to draw to our attention some of the sort of interesting properties of films and bubbles. Perhaps you'll be persuaded to go home and fill up your wheelie bin with soap solution and produce some of these frames and try and repeat some of these demonstrations to your friends and family. Soaps and detergents are the sort of commonest liquids that produce these films. But if you examine, say, your souffle under the microscope, it consists of a sort of foam with surfaces meeting at 120 degrees and lines meeting at 109.47 degrees. Also, I don't know if we have cavity wall insulation here, but if we do, a nice experiment is to open up the wall, look inside, and you'll see surfaces, 3 surfaces meeting along lines and 4 lines meeting at a point at 109.47 degrees. Ooh. Okay, there's one other important liquid that has enabled man to survive over thousands and thousands of years, which has all these interesting properties. Okay, and we've purchased some of this liquid at great expense, and now is an appropriate time to demonstrate some of its magical properties in the sort of traditional way. Which has been developed by our forefathers over thousands of years. Right? Here it is. Right? Now, on the top here we have a head, which under the microscope consists of lots and lots of bubbles with surfaces meeting at 120 degrees and lines meeting, 4 lines meeting at 109.47 degrees. So the next time you see your colleagues or professors taking some of this liquid for medicinal purposes, you could point out these magical properties, and I'm sure they'll make a speedy recovery. Thank you very much, ladies and gentlemen. Thank you.